everybody's there, so we can start the afternoon session. And so, okay, this morning you have seen Gilles and Chris started to give you some idea of the problems and the questions that we want to discuss, okay, in this school, but from the glass point of view and the computer science point of view. And now I think Giulio is going to start introducing a set of methods that you will see. Hopefully, they will be useful to address at least some of the questions that have been raised this morning. So Giulio is the right person to do that because he contributed a lot of ideas, and also he applied these methods to a variety of fields: quantum systems, classical systems, ecology now, machine learning. So and okay, so
it's okay. So thank you. Good afternoon. So as Francesco said, it's okay, the audio. So in principle, I mean, my job would be to give you, to introduce you to what are the concepts that has been developed, or let's say in what is called the mean-field theory of glassy system, and the methods. So I mean, it's a bit difficult, I mean, in 4 lectures to cover everything, and also I know that, I mean, there is heterogeneity in your background. So in principle, I try to prepare the lecture in such a way that everybody can follow. But then if you really want to learn deeply and try to understand and learn the techniques, it's possible, but you have to work more. And for this, I prepare homework, which I think are instructive and interesting. But this is up to you. So I will just start with a few slides. So about landscape. So you heard already that, that there are rough energy landscape in many different contexts. And here I wanted just to show you one very simple case, which I find always very interesting. So you take particles that interact with a very simple potential, which is this Lennard-Jones potential. So this one, repulsion at short scale and attraction at intermediate scale. So there is no quench disorder. And nevertheless, if you look to the energy landscape, so you move the position of the particle and you look how the energy change, what you find is that the energy landscape is very rough. And this, to me, there is no disorder, and finding this complex behavior which emerge from something in which, in principle, there is absolutely no disorder, I think is fascinating. And so one way, just to show you how rough is this energy landscape. So I will go quickly because it's not really the main topic of my lecture. But so here, imagine that you have a landscape like this. The fact is that the energy landscape is a function in a very high, dimensional space, because you can move all the position of the particles. So it's very difficult to represent what you get if you try to study this energy landscape. So this is a way which has been introduced by David Wales. So imagine that you have an energy landscape like this, as in one dimension. So I will draw it. So if I cut here, you see that all the position here, all are, let's say, connected. So I can go from any position to any other position without, having to go. What I want to say is that there is just one basin below this energy level, and I will represent this with just one line. Then if I put here the line, then I see that I'm disconnecting this basin with this basin from this basin, and so we'll draw 3 lines here, and so on and so forth. That's just intuitively what happens. And so here is what if you do numerics, is what you get for just 38 Lennard-Jones particle. So this is the tree that you get if you do an exhaustive study of the energy landscape of 38 Lennard-Jones particle. And what you see, it's not interesting in itself. What is interesting is that the number of minima that you get is 5,000 for just 38 Lennard-Jones particle. And now when we want to explain glasses, so the number of molecules that you have in a liquid which transform in a glass is something like 10 to the 23. It's not 38. So if you get 5,000 minima for 38 particles, you can think how many minima you get when you have 10 to the 23. And what we think is that we have something like 10 to the 10 to the 23. So really a gigantic number. So landscape, as you have heard, appear in many different contexts, actually, rough landscape. And this is very quick. It's just to show you that, this idea of rough energy landscape is around in many different fields, from biology, for example, on the problem of protein folding, or also the problem of evolution, even in high energy physics. And the thing which is interesting is that in the case of glasses, Actually, I mean, the real progress is that we have developed techniques to address and to study and to characterize this rough energy landscape. So it's not just a paradigm, it's just not an analogy. We can really study their properties and understand their universal behavior. And well, just to make you feel the difference, when you study crystalline solids, what you can do, I mean, you can study many different ways, but one way to do it is you just say what is the ground state, is a particle put in a periodic position in space. Okay, you can characterize how many crystal structure you have using the symmetry. As you know, there is a finite number of possible crystal structure. And then, well, you can you say, well, if I raise the temperature, then I have to study, I mean, how I have defects inside this crystal, and then you can construct the theory of crystal and in general of order matter. Now, if you try to do the same thing for glasses, then it's not going to work. So here, I mean, is an example of how particles are arranged in a glass in a numerical simulation. So it's just a very disordered way. And if you try to study the energy landscape, well, this is just a cartoon, but as I told you, you have a number of minima which is gigantic. So if you want to study, for example, what is the ground state? What are the low energy structure? How can you do it? You don't have the symmetry that guide you. And in principle, you should study this landscape. You should be able to find what are the minima. And if you want to study the dynamics, well, you have to understand how the system goes from here to there. So what are the barriers? I mean, what are the paths? And again, I mean, it's very, very difficult in the case in which you have really, I mean, the landscape is very rugged. So in a certain sense, we change paradigm. So in this case, we have a very simple energy landscape with few global minima. And here we have so many that what we have to do is to study the statistical property of the landscape. And this is what actually the mean field theory of glasses system is able to do. At least not in all cases, but in a very general subclass, it's able to, well, develop a theory of the statistical property of landscape. And what is nice is that, well, now you can make bridges between problem in computer science, in biology, or in glass theory, because actually the underlying landscape has the same statistical property. So this is what I would like to try to teach to you. Okay, so now we'll switch to the blackboard. Okay. Okay, so what we're going to do today is, so the first lecture is about, again, the simplest rough energy landscape possible. So let's call it, so rough landscape 1. And so what I'm going to do, I'm going to study the very, very simple model, but which actually is very rich and is used in many different fields, and is called the random energy model. So the random energy model, so let me define the model. No, this can go up. So in the random energy model, so what you have in mind is that, imagine that I want to do a theory of rough energy landscape. And let's say I'm naive, and I will do the simplest thing possible, but which is rich. So first, I don't take continuous degrees of freedom. Yes?
Sorry to interrupt, but you may want to write this on the board, because if that's going to be an important slide, you might want to then put it up and leave it up. Move to the right.
No, yeah, okay. No, I think this is fine. It's just introduction. That's fine. Okay, thank you. So the random energy model, so what I will going to take as the space of configuration, I will take as configuration Ising spins, okay, just to be as simple as possible. So a configuration will be a set of n spins. So let's say sigma 1, sigma 2, sigma n. Okay, so sigma 1 is plus or minus 1. So the number of configuration is 2 to the n. And then the system, I mean, if I think to, for example, in the Ising model, I know that, I mean, typically in the Ising model, if I have a certain dynamics, because it's important also to think to the dynamics, as Chris said, so there is not just the energy landscape, there is also how the system navigates through the dynamics, will be just, let's say, Monte Carlo single spin flip. So I take a spin at random, and then I flip it, okay? So this will be the configuration, which are the neighboring configuration to a given one. all the one that I can reach by a single spin flip. Okay? So, and now if I want to be very, very naive, what I'm going to do is that, in principle, what I expect is that in concrete systems, so in a realistic system, I have an energy landscape in which, the energy of this configuration will be, in principle, different from the one of this configuration, will be different, will be correlated. So what I'm going to do is I'm going to replace a complex system by a random one. And so this is the, so what I'm going to say is that, in generic systems which are complex, I have a very complex rough energy landscape. And now I replace this by a disordered one. And the disordered one is defined in this way. So at each configuration, I will associate an energy. And this energy is a Gaussian random variable. And I will take all energy as independent and identically distributed Gaussian random variable. Okay? Ask me a question if you don't know or you don't understand. Okay? And so it's Gaussian and it's average. So maybe I will write it here. So the average is 0, and the variance is n divided by 2. Yes. Okay?
Is this just an assumption, or there is a reason to believe that this is true?
No, there is no, in principle, no reason to believe that it's true. This is like, if you want, it's like the joke about physicists that take the cow and they replace it by a sphere. So, but in reality, the fact of replacing a complex system by a disordered one is a strategy which is very deep in physics. And of course, you cannot do, if you have a problem that you cannot solve, you can just replace it by a random one, because that's not going to work. But in many, many cases, replacing something complex, which contains a lot of degrees of freedom, by something which is disordered, has been right in many different cases. So in this case, it's not, there is no sense in which the random energy model is a correct model for a realistic system, but it will give us a lot of results, which will, then we will generalize.
So the raw statistics of these two configurations are similar. What histogram correlation do you have?
In general? Yeah, so in general, for example, I don't know, in liquids, people have, okay, well, maybe I will discuss this after that I analyze the random energy model. But the idea here is really, here I have a complicated problem, which is very, the landscape of, I don't know, a real glass or a real liquid is very complicated. Let's study the simplest case possible. And what we will see is that studying the simplest case possible, we will gain already a lot of information that then we can generalize. Okay? Yes?
So do you erase all of the information that is nearby systems?
Yes, yes. It's really the simplest, you can think is the simplest model of rough energy landscape. Yeah. When I flip a spin, the energy of the new configuration is just a Gaussian independent random variable. Yeah?
Can I imagine this procedure is like I partially trace out certain way of the system and such that maybe with some random variable, but it's actually simpler than the original one. I'm just curious, is there any more concrete way of connecting the complex to the disorder?
Okay, let me, yeah, it's, in a certain sense, you want the final answer before that. So let's study this, and then I will tell you how this can be generalized. So the only thing that I wanted to say is that replacing something complex by something which is disordered has, let's say, a long tradition in physics. Just to give you an example, to study very complex nuclei, Wigner, what he did is that he replaced the Hamiltonian, which was very complicated operator with many nucleons, by a random matrix. At the beginning, this could seem crazy, but actually he found results which were very good compared to experiment, and now we know that they are not very good. They are exactly what you should find if the number of nucleons is very large. Okay, so this was just to tell you that we are not doing a crazy thing. Okay, so if you are all right with the model, so let's study it. So we'll study it here. So the first thing that I want to do is, so now I will draw this. So I will draw this thing, this thing like this. This is the pictorial way of the energy landscape, which is always bad, because it's in one dimension, whether the energy landscape is many dimension and it's just a picture, but I mean, I have to draw something to discuss. And what I want to do in the following now is to compute how many configuration I have at an energy which is between E and E plus D. Actually, in general, what I want to do now is to study the energy landscape of the RAM. And so let me tell you just that the RAM has been introduced by Derrida in 81, and I will tell you, there are many different incarnations of this model in many different fields. There was a question? No? Okay, so, well, to study how is the energy landscape. So what I want to know now is, first, how many configuration I have between the energy E and the energy E plus D. Okay, so I will draw this. This is the number of configuration and E that I have between E and E plus D. Okay, let me write it this way. Sorry, this one will be the number of configuration which I have between E and E plus D. Okay, and so what is this? I will write it like, so what I want to compute is actually the average. Okay, we'll draw, this is the average with respect to the disorder. So what I mean is that I throw all the energies, and in this way I have a model. Okay, and then for a given model I can compute how many configurations I have between E and E plus D. And then I can, draw other energies, so construct another model. I have another value of this, and now I compute in the average. Okay?
So
yeah.
When you have such a disordered system that you define, how do you know that that landscape is continuous at all?
Well, here is not even, there is even not it's really, so first here I have Eisenspins, so there is not really a definition of continuity, and then actually is the more discontinuous as possible, this energy landscape. In the sense, as I said, if I flip a spin, the energy of the new configuration is random and uncorrelated from this one. In a realistic model, in general, if I move, just one particle, if I just flip a spin, I'm not going to change the energy very much. I will change a little bit. And yeah, so yeah, it's not continuous. But
there's not any problem that you write NE like that, the number of states at energy E, if it's very, very discontinuous?
No, because it just say, I have just imagine, I'm just counting how many points, how many configuration I have between energy E and E plus D. DE in general here will be always small, but much larger than 1 over n. No, in principle there is no problem. Okay, so let's compute it. So what is NED? I can write it like sum over I from 1 to 2 to the n. Okay, these are all the configuration. And then I put a variable yi, and yi is equal to 1 if the configuration, so I is the index for the configuration. So they say the configuration, I will call it Ci. If the configuration Ci has an energy, ECi, which is in the interval E plus D, and it's 0 otherwise. Okay? And then since I'm computing the average, I put an average here. Okay? Okay. So now, so first, okay, I can invert the sum with the average. So I have the sum from I from 1 to 2 to the n of the average of yi. Okay. Now all the energies are Gaussian random variable, identically distributed. So it means that this average of yi does not depend on I. All the energy behave in the same way. So actually this will be equal to 2 to the n yi, or y, okay? And now what is y? So y is the probability that if I take a configuration, its energy is between E and E plus D. So what is it? It's, so y, E is a Gaussian variable. So what is, y is this. So what is the average of y? Give me feedback, otherwise I will be scared, because I'm going to do much more difficult thing. No? No feedback? Yes. It's the probability that the energy is between E and E plus D. Okay, and what is it? So this will be the integral between E and E plus D of, well, the Gaussian law, which is exponential of, let's say, minus E prime square divided by n square root of Pn dE prime. Okay? If I have a Gaussian variable, which has the variance that I wrote, which is n divided by 2, this is the probability density, and this is just the probability that the energy is between E and E plus D. Okay? Now, dE, as I told you, is very small. So this will be just equal to 2 to the n exponential of minus E squared divided by n square root of Pn dE. Do you agree? I just replace, this integral, if d is very small, I can just write it this way. Okay. And now this, well, I can rewrite it in a way, well, maybe I change it and I write it here. So now what I get is that the average, so this one is the NE, dE. So it's 1 over square root of Pn. Yeah?
You might want to switch to the center ball.
Yes.
I think those guys cannot really see that.
Okay. Okay, so let me continue. So the average, so this n is not the number of spins, is the number of configuration, and so this will be 1 over square root of Pn. So it's I will transfer. If we put everything in the exponential, so I will have exponential of n log 2. So this is the 2 to the n minus n E squared. And in general, so now small e is equal to big E divided by n. So in the following, when I use a small letter, it means that I'm referring to intensive variable. Okay, so per degrees of freedom. These instead are the is the total energy. Okay. So what you see here, and the other thing that it's important is that when I'm doing computation in general, and now and in the following, I will be always interested in, so I will have things which are exponentially in big N, and then something which is of order 1, and I'm always interested in, let's say, in the leading term in exponential of n. Okay, so I will drop terms which are subleading with respect to this. So for example, in this case, I will say that this is, I will drop this, and is equal to exponential of big N of log 2 minus E squared.
What about the d?
Yeah, sorry. I should put the d. Yeah. Thank you. Yeah, but it's subleading again. Yeah. Okay? Okay, good. So now let's draw what is, let's draw this, I will draw what is here. So what I have here should remind you of something. So in general, if I have a system which is not a disordered system, what is this? So if I have the number of configuration between E and E plus dE, and I write it like exponential of the number of degrees of freedom times a function of E, what is this function of E? No, not really. Again, don't scare me, please. What is it?
The entropy.
The entropy, yeah, exactly. So now, in this case, we are computing the average of n. So, well, we don't know if this is really the entropy, okay? So I will draw this function. So this function, which is log 2 minus E squared, as a function of E, has this form. So here is my minus square root of log 2. Here I have square root of log 2. Okay. And now what I want to show in the following is that, so what we compute is the average value of the number of states that I have between energy E and E plus dE. Now what I want to, actually I don't want the average value, I want to know what happens if I take a typical system. So I draw the energy, I look at my system, and I want to know how it behaves. It's N of E. Okay? And what I'm going to show you now is that actually, for a system, what I will find is that here I will have, so in all this regime here, with probability 1, so with probability which goes to 1 when n goes to infinity, I will have no configuration. So there are no configuration with intensive energy less than this value, and there are no configuration with intensive energy larger than this value. And then if I consider the N of E dE for a given system, actually if I take, so let me take the log of this, let me forget about the dE, I take the log of this and I divide it by n. So this n is the number of degrees of freedom, this n, curly n, is the number of configuration. So what I will get is S of E, which is equal to log 2 minus E squared, when E is less than square root of log 2, sorry, yeah, with probability 1. So what I mean is that if n is this n, so the number of degrees of freedom is not very large, I will get a fluctuation here around this. But when n goes to infinity, if I take a typical system, what I will get, if I take its curly n, I take the log, and I divide by the number of degrees of freedom, will be exactly this curve. Okay? Okay, so this is the magic of, with random variable, I think you know already, for example, the example of the central limit theorem. When you take few random variables, you have complicated behavior. When you take a lot of random variables, somehow deterministic effect emerge. And so here is an example. So here we will not have fluctuation. And so this is really will be really the entropy of my system. Yeah.
This is essentially Wigner's semicircle?
No. No, I will discuss tomorrow Wigner's semicircle, but no, this no. It's a parabola, actually. Other questions? Yeah?
Can you relate this a little bit to just some comments to like more realistic models of like random spin models, like random field, random bond models? Like,
yeah.
Those will translate to some random energy.
Yes.
Features, you know, how many features of this random energy model reflect this, or, you know, more physical or shorter?
So I mean, would require a more longer discussion. So something that is really important in a realistic system is that energy are correlated. So this is really something important, and which is missing here, in the sense that if I'm in a configuration, if I change it slightly, I'm in a new configuration, but the energy of the new one, well, it's a random variable, but it's correlated. So it means that the landscape is not changing widely, but it's changing more softly. So this is, I think, it's the most important thing. Now, one can discuss about the fact that here I have a parabolic behavior. Well, for example, for supercooled liquids, there are simulations that, I mean, seems to suggest that this parabolic behavior is not too bad. But okay, I should discuss really in detail depending on the system. Yeah.
But there's some features of this that are supposed to emulate more realistic.
I think this is the
Yep.
zero order.
Yeah. It's really, I don't want to put this model as. So let's say, I mean, the things that which I would like to arrive, but maybe not in this lecture, but at the end, is that, I mean, statistical property of landscape are universal in a certain sense. Exactly like if I want to describe a liquid-gas transition, well, I can take a stupid model of a ferromagnet, a very stupid, which is very different from realistic material, for example. But this stupid model will be, within mean field theory, correct for the ferromagnet. It will be also correct for the liquid-gas transition. And so here, the property of that I will get from this model will be common to many other systems, which are more realistic, more complicated, but still, we still get something from this. OK, so let's now try to show. I want to show these two things. Here, I don't have any configuration. And here, this curve tends to this, to this log 2 minus E squared when n goes to infinity. OK? So let me see now what I'm going to erase. OK, I will do it here. OK, so there are two things. This is the first one, and this is the second one. So first, no configuration. So now I'm considering the case in which the energy is larger than, so in absolute value of square root of log 2. Okay? And what I know here is that in this regime, the average value of, let's say, of the number of configuration between E and E plus dE goes down, is exponential of minus a positive constant time big N. Okay? So this goes to 0 when N goes to infinity. Okay? And very fast. And now, well, I will write, okay, what is the probability that I have one configuration, at least one configuration, so at least one, let's say, configuration with an energy, with an intensive energy, which is larger than square root of log 2. Okay? So maybe actually I will put it this way. I will the probability that at least one configuration has energy EC between E and E plus dE, and E is taken in this way. Okay, so I'm looking to the probability that I have one configuration inside here. Okay, so this will be the sum, small n larger than 0, of the probability to have n configuration in this interval. Okay, so I say it again. So the probability to have at least one configuration inside this interval is I sum over all the possible cases. I don't want the case n equal to 0, in which there is no configuration. Then I can have n equal 1, n equal 2, and whatever. Okay? Okay, good. So this thing is less or equal than the sum over n from 0 to infinity of small n p of n. Okay, do you agree? Because, well, when n is equal to 0, so I don't have the n equal to 0 term. When n equal to 1, I have the same term. And when is equal to 2 or 3, well, this one is bigger than this one. It's okay? And what is this? What is this thing? So this, I'm computing, I'm summing over all n, and for each n, I sum over the probability to have n configuration between energy between E and E plus dE, and I multiply this by n. Is the average of n, yeah. And how the average of n behave? Well, we know it from here. It goes like exponential minus C of n when n goes to infinity, so it goes to 0 when n goes to infinity. Okay? So this means that when n goes to infinity, with probability which tends to 1, I will have no configuration outside the interval. Okay? Okay, good. So now I would like to prove the other, or to prove, well, actually, no, to argue that in this regime, instead, we will get this S of E when n goes to infinity without fluctuations. Are there questions on this? Okay, so now, well, to do, so this was step number 1. So step number 2 can be done rigorously, but I will not do it, even though it's simple. I will just argue. Okay, let me see that I'm not forgetting anything crucial. Okay. Okay, so step number 2. So what I'm going to do, so how I can show that, I mean, being a physicist, or I mean, be simple-minded, what I should do to show that the fluctuation goes down if I have a random variable. Compute the variance, exactly. So let's compute the variance. So what I want to compute n e dE square minus n. Sorry?
I don't think anybody can see what you're writing over that.
I see. So the problem is that the other boards are not.
There's a one behind it.
Ah. Great. Thank you. Okay, so let's compute the variance. NE dE square average minus average of NE dE square. Okay? Okay, so let's go. We can go do it slowly. So what is this? I mean, if you remember, I wrote it at the beginning. This, I wrote it like sum over I of yi, where yi was my variable, which was 1 or 0. So it's sum over I of yi square, average, minus, here I have sum over I, yi, average, square. Now, let's go. So I have sum over I and j of yi, yj. Well, let me, okay, I will do it in 2 steps. Minus sum over I and j of yi average, yj average. I hope it's okay. I mean, I do it a little bit fast. So what is this? Well, this is sum over I and j of yi, yj minus yi, yj. Okay? And now, since I know that the energies are uncorrelated variable, so this, for I different from j, is 0. Okay? So this means that the only term that remains is sum over I of the average of yi square minus average of yi square. And now I have a problem with the board. But so, well, so I think if I write below this, it's not visible for the people in the back, right? No? It's okay? Okay. Okay, so I will do one line, or maybe, no, I will switch board. You go here. Okay, so let's do this computation. Okay, so sum over I of, let's say, yi square minus yi average square. So now, what is the average of yi square? So if you have to compute it. Since yi is a variable which is 1 or 0, so I can simplify it. I can take the 2 away. Do you agree? It's 1 or 0, so 1 square is 1 and 0 square is 0. Okay, so let's write now what is this. As before, these average are independent of I. So what I get is 2 to the n, the same value. And what is this? This we computed already before. This is exponential of minus e squared divided by n square root of pn dE. This is the first term. And then we have the other ones, which is just the square of this. Okay? This is minus e squared divided by n square root of pn dE squared. Okay? And now I'm looking at energies which are, let's say, here, let's say, different from 0, so in this range or in this range. So this means that this thing here scale with big N. Okay? So this, yeah?
Does it matter that you've got one term in dE and the other term in dE squared?
No. No.
You want to say why?
I mean, well, in any case, dE is, so it's something that I should take as small, but that does not scale with n. Or, I mean, well, except if I want to do very, let's say, detailed things. So no, I mean, I'm just computing the fluctuation of NED. And in any case, again, I'm interested to the exponential order, and to the exponential order, I just don't care about the dE. Okay, so what you see here now is that here I have, so this thing here is exponential minus something which scale with n, square. Here I have the same thing, but it's not square. So this thing is much smaller than this. Okay, so this I can forget. Okay, and so what is this? Well, this is just our friend, the average of NE dE. you remember? Is 2 to the n, the same thing that we computed before. Okay? So what we get now is that in that regime that is there, so if I compute the n square e, sorry, an EDE square connected, okay, so the variance of this scale like an EDE. Okay? And so now we can conclude. Why? Because what we want to know is how this variable, so let me write it maybe. So what we want to know is how this variable an EDE behaves. So it's a random variable, so it would behave like its average, an EDE, plus fluctuation. So what is the strength of the fluctuation? Well, it's the square root of this. Okay? So the fluctuation will be of the order of square root of an EDE, average. Okay? So this is exponentially large in n, and so this will be much smaller than this one. Okay? So this means that if what I'm interested in actually is this entropy, so S of E. Well, I can forget. I mean, the fluctuations are much smaller than the average, so this variable is not fluctuating. Okay? So this just, well, it's an argument, but you can really prove it. I mean, there is an inequality, general inequality in probability theory, which is called Chebyshev inequality, which, I mean, allows you to write this in a more rigorous way. But I think it's enough for us. Questions? So fluctuation, yeah.
At the first place that you were defining the variance of E,
yeah.
Why did you choose it to be proportional to n?
Okay, yeah, that's a good question. So it's because when, in general, I had, so it's, in principle, since I want to describe a, let's say, many-body system, so interacting degrees of freedom, I have to make a choice of how the energy, which is a random variable, scale with n. And so, well, there are two answers to your question. The first answer is, first, I can do it in this way. I choose n to some power, and then I fix the power in such a way that everything is well-defined. So, for example, I want that, I mean, this n of E scale like exponential of n times an entropy.
Yeah,
that's, yeah, exactly. So this is one answer. The other answer is that I take a realistic system, I don't know, random field Ising model, and then I compute the variance of the energy, and I see how it scales. It scales like n. So it's better to do the same. Yeah, so these are two ways to do it. Okay? Okay, so now what we know, and again, don't hesitate to ask me questions, is that here we don't have configuration, here we don't have configuration, and here we have that the entropy of our system is exactly given by this equation. Okay? Okay, so this already tells us something about the energy landscape, but still we don't know, I mean, the energy between E and E plus dE, are they minima? Are they well, maxima probably not. But, I mean, how is the energy landscape? So now we would like to study a little bit more how is the energy landscape, if there are no questions. Yeah?
So if I understood correctly, you're taking the averages over ensembles of your energy relation. But is this system also self-averaging that is large enough?
Yeah, so this actually is what I proved here, actually, is that when n is large enough, well, the entropy is not fluctuating, for example. Yeah. Other questions? Okay, so now what I want to do is to, yeah.
Would it be fair to say that this is basically a way of demonstrating that central limit theorem holds for this system?
Sorry, a way to?
Would it be fair to say that this derivation is a way of demonstrating that the central limit theorem holds for this system?
Well, yes and no, in the sense that it's true that, I mean, if you compute, I mean, how many energy levels I have inside here, this is a sum of independent variable. The fact is that for the central limit theorem, in general, your variable doesn't have statistical property like the variance or other things that scale with n. In general, you have n variable, and the statistics is fixed. Here, instead, we have something which is mixed. And when something is mixed, so you sum independent variable, but the variance of this variable, or I don't know, the other moments scale with n, actually the central limit theorem sometimes cannot hold. So it was not completely trivial. Yeah. Okay, so now I would like to describe the property of this landscape. So are the energy between E and E plus VE minima or something else? Okay, so now I'm here. So I know that, actually now I know how I can call this. This is the energy of the ground state. It's the smallest energy that I find in the system, okay? And now I'm here, and I'm in my drawing, which is like this. So I'm here, and I want to know what are these configurations that I'm counting, okay? So let me draw in this way. So I have my energy here. So here I have the 0 level. What I know from the computation that you have done there is that the majority of the configuration are here, okay? Because the entropy is maximal at energy 0. Now, if I go down, I still have an exponential number of configuration, but they are much less than this one. Let's say that I take one configuration at random between the configuration which are here. So let's say a configuration which is right here. And then, I mean, if I take a configuration, what are the neighbors of this configuration? So again, if we think to all dynamics that we use in spin system, so in the usual dynamics are spin flip. So if I have a configuration, all the neighboring configuration are the one that I can reach with the one spin flip. So how many neighboring configuration do I have? Big N, exactly, yeah. And now, what is the typical energy of this neighboring configuration? So let's say typical intensive energy. Yeah. Yes? I mean, go ahead. Yes, it's 0. Or if I want to keep the big N is 1 over square root of N. So I have my typical neighbors are here. And here means order 1 over square root of N. But now you could be, you could be subtle and you could say, yes, okay, if I take a typical, so if I take one neighboring configuration at random, its energy will be 1 over square root of N. But now I have N configuration, then maybe I have one configuration which is atypical, which is an energy which is much smaller, okay? And so, it's important to understand, the statistical properties is that now I have that my neighboring configuration are N random variables, Gaussian random variables. And so I would like to ask what is the minimal energy between all the neighbors, okay? So what this means is that I have N Gaussian independent variable. What is the value of the smallest one? So how many know how it scales, or at least how you can derive how it scales? Can you raise your hand? Good. There should be some people that follow my lecture at the École Normale that should raise their hand. Okay, well, so this I will not do it here, because otherwise I don't have time to do more interesting things. But if you have, and it's very easy, so think about it, and then we can discuss later. So if I have N Gaussian random variable with average 0 and variance 1, then the value of the minimal energy, so I will now is E min, will be minus square root of log n plus fluctuations. Now the fluctuations are subleading with respect to this, okay? And we know, one can find what is the law for the fluctuations, but we don't care. So the typical scale is this one. This is if you have Gaussian variable which has a variance which is equal to 1, okay? In our case, the variance is equal to n divided by 2. So the typical scale of the random variable is square root of n divided by 2. So I have to insert here square root of n divided by 2, okay? Okay, so this doesn't change too much, because you see that now the intensive value of the minimal energy between all my neighbors will be just minus square root of log n divided to n, okay? So it's a little bit smaller than this, but not so much, okay? So we'll put it here. This is the minimal energy, okay? So what this means is that if I look to my landscape, so when I look to configuration which are here, so at intensive energy which is less than 0, this configuration, typically all their neighbors are very, very high. So intensive energy, which is 0. So this is really like a golf course. So it means that, well, if you want, if I walk here, well, I have all configuration which are more or less at the same height, and then sometimes I have one, which is very deep, okay? And typically, if I take a configuration at random here, will be a minimum, a local minimum. So what you see here is that in this landscape, you have an exponential number of local minima, and actually all these minima, all the neighbor of this minima, they just go up until energy 0, okay? Questions? Okay, so this clearly comes from the, I mean, you see you have some drastic property of this energy landscape. So in normal energy landscape, you don't have this property that if I'm deep in the energy landscape, I will have to go very, very up to go down again. So this is due to the fact that neighboring energy are uncorrelated. But, well, this is what we get in this very simple case, okay? So now that we have described the energy landscape, what I would like to do is to study the thermodynamics and say a few words about the dynamics, and then make the connection with supercooled liquids. Okay? So let's go. So maybe I can write this because it's always a golf course landscape. Okay, so let me check that I didn't forget anything. Okay, so let's go and study now the thermodynamics. I will do it here.
Probability of these, the holes in
Yeah.
the course, that's the exponential or Gaussian probability.
This is the exponential of n of SE. Yeah.
Right.
So yeah. Yeah. So now let's say 2 is the thermodynamics of the RAM.
Sorry, it's the tails of the original Gaussian, isn't it? The distribution of the.
Sorry.
It's the tails of the original Gaussian distribution of the
Yes.
energy model.
Yes. Yes. It's really the typical energy are order one, well, are close to 0, but then the tail, since you have so many configurations, that you sample the tail of the Gaussian. Yeah. Okay, so now what I want to do is to compute the thermodynamics, just to study how the system behaves when at a certain temperature. Okay, so what I have to do, I have to compute the partition function. So I have to sum over all configuration, and then I have to do exponential minus beta EC. Okay, the energy of a configuration. Okay, so now this, I can always rewrite this in this way. So I have the integral over, so now I pack together all energy, all contribution which come from energy which are between small e and E plus dE. So let me say in words what I'm doing. So I rewrite this like the integral over dE of n curly n of E. So this is the number of configuration between E and E plus dE. And then I have exponential minus beta small e big N. Okay? So this is the contribution which comes from all the configuration which has an energy between E and E plus dE. Okay? And the integral should be between minus square root of log 2 and square root of log 2. Okay? Because I know that when I take a sample, well, I know that there are no energy, there are no configuration which energy which are below this value and above this value. Okay? It's fine. And now what is this? Well, let's rewrite it. It's again the integral between minus square root of log 2, square root of log 2 of exponential of big N of what? Of, well, S of E minus beta E dE. Okay? And now, well, you see that since I have to do this integral, but now n is very big, so what I have to do, well, with how this function behaves. So this function, if I draw it, let me draw it, well, this way. So this function is very, very big, around its maximum. Okay, this is E, and what I'm drawing is this function. Okay, so this function will have a maximum, and close to the maximum, I have something which is exponential n to something, and if I go farther from the maximum, I have something which is, I mean, the things which multiply n is smaller. Okay, so this is going down, like I mean, if I compare this to this is exponentially smaller in n from this point. Okay, so the value of this integral is in principle given by two things. Either, so it's the exponential of n of s E max minus beta E max, where E max is where this function has a maximum, if the maximum is inside the interval. Okay? Of course, if the maximum of this function comes for energies, so imagine that here I have my minus square root of log 2, then in this case the integral is given by this maximum, but if the function is maximal here, well, I don't have configuration here, so what I have to take is the value at the boundary of the integral. Okay, so what I will get is this, if the E max is less than square root of log 2 in absolute value, or otherwise I have exponential of n s of E ground state, which is 0 actually, so I drop it, minus beta E ground state, if the maximum is outside square root of log 2. Okay? And so let me say it in words that maybe are more familiar. Yes, just a moment. I say this and then you can ask. So I hope you can. So what I have to do to compute the log of z, sorry, yeah. So what you know is that the logarithm of the partition function in any physical system, what is this? This is minus beta big N times the free energy. And this in general is equal to the entropy, sorry, big N times the entropy minus beta E. Okay? And what you know is what you have to do if you know the entropy to get the free energy of the system, you have to, well, minimize the free energy or maximize minus beta times the free energy. So you have to take the maximum of this, but of course, I mean in the interval in which you have configuration. So the entropy must be positive or 0. Okay? So in this is the is this. There was a question? Yeah.
Could you have taken, if you had taken the microcanonical entropy you calculated before, would you have obtained the same thermodynamics?
If I had taken the microcanonical.
I mean, this is the expression for the entropy as a function of the energy.
Yeah.
So you take the derivative with respect to the energy and get 1 over temperature.
Yes.
And presumably it gives the same.
Exactly. I will do it just now. Okay. Yeah. So indeed, I mean, now I have this thing. So this is what I should do. Well, let's do it. So let's see what is the maximum and how the maximum behave as a function of temperature, which is what Patrick is saying. Questions? This should be fine, I hope. Okay, so again, I switch blackboard. So this I cannot use. No. Okay, well. Okay, so let's do the thermodynamics. Sorry?
You can do the middle one. You can push the middle one off.
There is a second one, or? Okay, I can write here. Okay, so let's do really the thermodynamics. So I have my entropy, S of E, and what I want to do is to find the maximum of this. So find the maximum is I take the derivative of this, and I put it equal to 0. And, well, surprise, what I get is S prime of E, which is equal to beta, which is the usual relation between energy and temperature. And now let's do it explicitly. So S of E is log of 2 minus E squared. So this equation is minus 2E equal to beta, which means that the energy is minus 1 over 2 divided by the temperature. Again, this is true as long as the energy is not too low. Okay? And I will do it also in a graphic way, which is useful for the following. So here I have my S of E. And now this equation, S prime of E equal to beta, means that if you give me a beta, you give me a temperature. What I have to see is, well, what is the energy, the value of the energy, in such a way that if I take here the straight line which has a slope beta, I find a tangent of the curve. Okay, so this will give me the energy which corresponds to the temperature, to the inverse temperature beta. Okay, and now if the temperature is very high, beta is very small, so I'm here. I'm, let's say, infinite temperature. I have energy 0. Then I decrease the temperature. Beta becomes larger and larger, so the energy goes down and down. And then at a certain point, I reach this case here, in which I have the same slope. And that this will be beta critical, or 1 over the critical temperature. And we'll see why this is a critical temperature. Because, well, here what I have is that the energy follow actually this law. So I have the energy, well, this I will draw it here. So let's draw the behavior of the energy. Energy as a function of temperature. So what I get something which goes like this. It's minus 1 over twice the temperature. In principle, it diverges at temperature 0. But when I reach the energy of the ground state, then the energy stops. Okay? So this is the behavior of the energy as a function of the temperature. So it goes down, and then when I reach a ground state, it stops. So this is what I get. Okay? Now you can also compute the specific heat. And I am saying this just because it's interesting for the following. So the specific heat, which is dE dt. So the specific heat, dE dt, which is equal 1 over 2 times T squared. As a function of temperature, it will go up. And then when I reach the critical temperature, which is here, then it drops to 0. Okay? Because, well, when I'm in the ground state, the energy doesn't change with the temperature. Okay? Sorry, here I should put E ground state here, and the critical temperature here. Okay? And what is the value of the critical temperature? Well, I can find it from this relation. I know that the energy of the ground state is minus square root of log 2. So from this, I get the Tc. Well, I hope you can see it here. Tc is equal to 1 over 2 square root of log 2. Okay? At this temperature, I reach the energy, which is the energy of the ground state. Tc, for people in the back, Tc is 1 over 2 square root of log 2. Okay? And now the free energy, if I want to say what is the free energy, well, I can also do it. So the free energy is equal to what is minus 1 over beta. I will just use the equation, which is the usual equation, which is here. Okay? The free energy is minus 1 over beta, and then I have S of E minus beta of E. So will be just so S of E max minus beta of E max, which I won't do well, I think I skip the computation, even though it's very simple. No, well, okay, I will do it. Okay, so what is S of E max? So it's minus 1 over beta, so log 2, minus E square. So E square, well, what is E? E is minus beta divided by 2. So let me write it here. I have log of 2 minus E square minus beta E. E max is equal to minus beta divided by 2. Yep. So you just replace. So I have log of 2 minus beta squared divided by 4. And here I have minus beta times minus beta divided by 2. So I have plus beta squared divided by 2. So what I get is minus 1 over beta log 2 plus beta squared. And this is true as long as t is larger than Tc. Instead, if t is less than Tc, what I get is minus 1 over beta times, this is 0, this is minus beta Emax. So I just get Emax. Sorry, the E of the ground. Sorry, this is the E of the ground state for t less than Tc. Okay, now I stop and you can ask me questions.
So that is also if we can equilibrate the system given at this.
Yes, that's a good point. I will come to this in a minute. Yeah, indeed. In principle, we cannot equilibrate the system until Tc. So what's going? Well, I will discuss what happens if we cannot equilibrate. But yeah. Other questions? Sorry, say it again.
So when you transfer the integral into that single value, maximum value, right?
Yeah.
But should you do the integral, but use the approximation of.
So what I mean is that, yeah. So if what I'm saying is that I'm doing what is called, it's the saddle point method or the Laplace method. So here I have a function which is exponential of n times a function of e, and so this integral. So let me say in this way. So what I'm using is that the log of the integral of exponential of n of f of x dx divided by big N is equal, when n goes to infinity, to f of x max if x max is in the interval of integration. So what it means is that, yeah, when you do this integral, so this integral which is here will be exponential of n of f of x max. And then there will be correction, but the correction are subleading with respect to this term. And since what I'm doing is I'm taking the log and divide it by n, I just drop them. And what I get here, well, in a sense, you see, it's really what you see in thermodynamics, the relationship between microcanonical ensemble and the canonical ensemble. So I can work either in the microcanonical ensemble, so somebody give me S of E, and once I have S of E, I can have a relationship between the energy and the temperature, and I can construct the free energy. Or I can start from the partition function, write the partition function as an integral with the entropy inside microcanonical entropy, and then I take this other point. Okay? Questions? Okay, so now, I said something about the thermodynamics. This is the thermodynamics of the RAM. I will just say a few words, really just a few words about the dynamics. So the dynamics of the RAM has been studied a little bit less. Actually, there have been several mathematical papers recently on the dynamics of the RAM. And I will not tell you much. The only thing that I want to tell you is that as we studied, the energy landscape of the RAM is very much like a golf course. So if I have a configuration here, this configuration is, all the neighbors are up. So what you can think is that the dynamics is going to be very, very slow. What I mean is that imagine that I want to equilibrate the system at temperature T. So at temperature T, the system will be at an energy which is minus beta divided by 2. Okay, but it has to arrive to this energy. And to arrive to this energy, typically it moves in the energy landscape. Then it tries, so it moves here on this level. Sometimes it finds a configuration and it goes down. But then, all the neighbors of this configuration actually are up. So, to go more deeply, what it has to do is has to go up again, which takes a long time because the barrier, the energy that it has to jump, it's of order big N. So it has to go up. And then again, it wanders around, and then it has to find another minimum, which is deep down. And so, the dynamics is like this. Okay, so it's very, very slow. And actually, I think it's maybe this week. I will post a paper on the archive exactly on the dynamics of the RAM, so you can look at it if you want to know more. So for the moment, just that the dynamics is extremely slow, like the one of glasses. Okay, because the system has to move in the energy landscape and to go. If it wants to go down more, it has to go up more and then go down even more. Okay? Yeah?
the dynamics, what are you taking? You're diffusing through those states?
Yes, I will say that. I mean, I gave a, let's say, matrix structure to the problem, saying that if I have a configuration, I have the n neighboring configuration, which correspond to the, let's say, to the n spin flips that I can do, and then I can take a single spin flip Monte Carlo. So I try to do the move. If the energy is lower, I accept the move. And if the energy is higher, I accept it with probability exponential minus beta e. But actually, it's not important. As long as the dynamics is reasonable and verify the tail balance, it will be.
It's local in the real space.
It's local in the real space, which means that in configuration space, you can move, but you cannot go to any other configuration. You can just go to the n neighboring ones. Yeah. Yes?
So this is a second order phase transition, right? This goes thermodynamically.
Yes. So the question is, what is the order of the transition? So yeah, so this was a point which I hope that Gilles could say something about, but no, he didn't yet. So yes, the property of the transition. So if you look to this transition like this, it's a second order phase transition. However, if you look to the dynamics, and this I think will be discussed, maybe I will discuss it more than in 2 lectures from now. Well, it looks like that if you try to define an order parameter, actually the order parameter makes a jump. So it has some property of the first order transition. So some people call it mixed phase transition. But to discuss why it's mixed, I should say something about the dynamics. So if you just look to the thermodynamics like this, it's second order, okay? But it's not as simple as that. So we will see that it's not a standard second order phase transition, okay? Okay, so what's happening? Maybe I can describe what is this phase transition. So I have my energy landscape that I draw in this way, which now you know that it's a very misleading way to draw it. So if I'm at infinite temperature, the system will be here, okay, at energy 0, intensive energy 0. So it means that the typical configuration which are sampled from the system are here. Then if I go down in temperature, I have that the typical configuration which are sampled by the system are here. We know that they are typically minima. And then at a certain point, the temperature is low enough, and then I start to sample really the bottom of the landscape. And then, so the difference is that here I'm sampling an exponential number of states. Here the entropy is finite. And at this point, I just sample a number of configuration which is no more exponential, okay? So what happens at this transition is that I go from a regime of temperature in which the entropy is finite, and at the transition, the entropy goes to 0. So this is why this is called an entropy vanishing transition. Okay, so it's the, yeah, okay. So now, well, what about glasses? So is the relationship, for example, what one can see in let's say, super cool liquids that approach the glass transition? And in generally, if I look to this system, again, as you asked, well, in principle, well, the system, only if I wait really long enough, it will be able to sample equilibrium configuration at temperature T. What's going to happen, like if I just take a system, let's imagine that I decrease the temperature, as Gilles said the experimentalists do in a real supercool liquid. So they have the, let's say, the temperature of the heat bath, they decrease the temperature, so the system can follow adiabatically, is at equilibrium, is at equilibrium, is at equilibrium. At a certain point, it takes so long to equilibrate that it goes out of equilibrium. So what it means is that when I decrease the temperature of the heat bath, the system is able to follow until a certain temperature at which it's not able to follow anymore, because actually to go from one configuration to a configuration at which the system should be, if it was equilibrated, it takes a time which is too long. So the system remains stuck at this level. Okay? So what this means is that now if I look to the thermodynamic properties, here, well, the system, what we'll do is that we'll follow this line until a certain temperature at which it falls out of equilibrium. And when it falls out of equilibrium, well, typically, at least in first approximation, it doesn't move anymore. Okay? And well, actually, if I wait long enough, maybe it's able to decrease a little bit the energy, but not much. So this, should remember you a little bit the energy as a function of temperature that Gilles drew today, which was different, but not so different. So it was something which was like this, and then there was the equilibrium branch, and then here there was what happens around the glass transition, defined as, well, what happened in experiments. Okay, so this is what would happen in a, let's say, a simulation in the random energy model. So the system follow at a certain point goes out of equilibrium, and this will be the glass transition temperature of the RAM, which is a crossover. Just depends how long you can wait, which is not, and so this is not, the critical temperature. Would be the critical temperature if you can just wait long enough, so very, very, very long time. Okay, and the specific heat is the same, so the specific heat, it will go up, up, up until here, and then at a certain point, the energy doesn't change anymore. I fall out of equilibrium, and so I get this. Okay, so this will be TG. And now, the interesting thing is that this, let's say, three properties: this behavior of the energy, this behavior of the specific heat, and also this behavior of the configurational entropy, is something that, well, you see, or at least, the energy and the specific heat is what you see, is the behavior that you see in supercooled liquids at the glass transition. So the energy really, does, as I told you, it goes down, and then at a certain point, it changes slope. So here, you don't have you don't have an horizontal line. This is just because in the random energy model, once you are stuck in one configuration. In a real liquid, once you are stuck, you can still vibrate. The particle can still vibrate. So you're stuck around one configuration, but you have some residual entropy. And so the energy can, just change slope. Okay? The specific heat, this is something that people see in experiments, and it's something which is very well known, is that there is a specific heat jump of something of the order of kb at the glass transition temperature. And this is actually an experimental important fact. So these two things are very similar to what you see in experiments. And actually, this idea that I'm telling, we just discovered for the RAM, the fact that the transition in the RAM is due to the fact that the entropy of the configuration which are sampled by the system goes down, down, down at a certain point because it becomes zero at the transition, was an idea that was already in the glass literature, okay, and was said in a different way, but it was already discussed, and I think Gilles is going to discuss it next time, okay. So and this is really comes directly from the model, but it was already there. So these three things start to say that, maybe we are on the right track. So the property of the landscape that we are discussing are rather good. Of course, this is a caricature of a real rough energy landscape, but still many, many properties that we get are right. Okay? And so what I'm going to do in the following is I'm going to describe more rich and difficult model in which, the property of the energy landscape are a little bit different, and they are more closer to what you see or you think, or some people think you can see in supercooled liquids close to the glass transition. Okay, so I would like to finish with two. So let me check if I said everything. Yeah, with two things. So the first thing is about the random energy model. So the random energy model, as I told you, I introduced this model as the simplest model of rough energy landscape, and actually. Since it's a very simple model, but still, you see, you get things which are qualitatively right if you compare to experiments. Actually, it's a model that has been, let's say, introduced or discovered or rediscovered in many different contexts. So it has been introduced by Derrida in 1981 to describe glasses and spin glasses. Well, actually both, but now we understand that it's a good model for glasses. But it has been used by, in particular, Walliness to discuss protein folding. It's used in a different version, which is called House of Cards, for people that study evolution. And as you will see, it play a very important role in computer science. So, again, it's a very simple model, but you will see it will be discussed, for example, by Guillaume Semerjian. It enters when you discuss, for example, error correcting codes. So it's a very simple model, but it's a paradigm for many, in many different fields. Okay? So are there questions? Otherwise, I want to Yeah, maybe let me just finish. Okay, no, I take question and then I would like to say a few things about the replica method. Yeah.
When you discuss the golf course engineering, can you explain again what the E mean actually is?
What the?
What the E minimum is?
So E minimum in the golf course is the minimal. I mean, so I have my energy landscape. I know that I have many configuration here, but I know that below E min, which is equal to minus square root of log 2, I don't have configuration anymore. So it means that, okay, let me draw it. Well, okay. So it means that here I have many configuration. Then if I go down, I still have an exponential number of configuration, but I have less. And when I arrive here, I have a number which is not exponential anymore. So I just have a few. And if I go below this, I have 0. So this is really the bottom of the landscape. Other questions? Yeah. This I add. Yeah, I will discuss it in 2 lectures. So it's yeah, okay. Maybe I can tell you, but I will come again on this. So imagine that I take a configuration at random in the landscape, and then I take a second one, and I ask, will this second configuration fall in the same minimum or not? So you see that as long as I have an exponential number of configuration, if I take one at random, I will fall here. I take a second one, and with probability 1, I will fall somewhere else. When instead I'm here, I am the bottom of the landscape, I take one, and the other one, while with high probability, will fall, let's say, in the same one, at least with finite probability. So this is the order parameter. And this order parameter makes a jump at the transition. So this is why the transition has some property like a second-order phase transition from the thermodynamics, but if I look to the order parameter, it's more like a first-order phase transition. But I will discuss it more in 2 lectures. Other questions? Yeah?
Does this model have saddles anywhere?
Yes.
Minimum and maximum?
Yeah, it has saddles. So, so for an Ising system, it's difficult really to define saddles. I mean, for a continuous system, it's clear how to define saddle. You take the Hessian and you diagonalize the Hessian. For spin system, it's less clear, but you can ask, if I take a configuration at random, can I have 2 neighbors which have an energy which is lower? And you can do the computation. The answer is yes. But the fact is that, so if I take a configuration here, I know that the majority of the configuration which are here are minima. They are in an exponential number. But still, there is an exponential number, but which is much less than the other one, of configuration, which are, let's say, saddles, quote-unquote saddles. So, and actually, tomorrow we will discuss a more, let's say, rich and complicated landscape for a system with continuous degrees of freedom, and we will compute also the distribution of saddles. Other questions? Okay, so let me just conclude in 5 minutes about the replica method, because this is the introduction to the homework. And let me do it there. Okay, so as I told you, so we use this idea in the case of the random energy model that we want to study rough energy landscape, and we study actually disorder systems, so energy landscape of disorder system. So this is what historically happened at the beginning, so this is how people start. What we understand now is that, I mean, there is no need actually to study really a disorder system. Also, a system which has no quench disorder can have rough energy landscape, and I gave you an example just at the beginning of the lecture, okay? But, I mean, it's much easier actually, if you want to study the properties, to study disorder system first. And then, at the very end, you can show that systems which are not disorder have the same property. But historically, and also is what I'm going to do, is we're going to study disorder system first, okay? And so when you study disorder system, well, since the system is disorder, so for example, the partition function fluctuates. The free energy, in principle, could fluctuate. So what you want to compute to study the thermodynamics of the system typically is the free energy. So it's the log of z, the partition function, divided by n, okay, which is equal to minus beta f, the free energy. So since this, in principle, is a random variable, you would like to compute its average. So now we'll put the average, I will denote the average with the over bar, okay? Before I put the bracket, but from now on I will put the over bar, okay? So what you can show is that the free energy is what you want, if you want the thermodynamics. And also, the free energy is a non-fluctuating quantity, so it's a self-averaging, exactly like the entropy I discussed before. So it means that if I take a random, a disordered system, I look at its free energy, while the free energy will be equal to its average value plus fluctuation, and the fluctuation goes to 0 in the thermodynamic limit, okay? So if I want the free energy, what I have to do is to compute this, its average. So how I compute the average? So this idea, so the replica method, it's a way to do that. So the problem is that the things that we are able to solve in general, so let me say how you do it. So you have to compute the log of z average. So the trick that you use is that this is difficult to compute. What is easy to compute are moments of z, this random variable. So what you do is that, no, I can't use this. So you use this equation, which is that the log of z average is equal 1 over n, small n, log of z to the n average when n goes to 0. Okay? So let me just first, well, I will discuss this later, but let's first prove with this. Okay, let's do the computation. So this, let's see that is true, is 1 over n, the log of, so z to the n average, this is exponential of log z. Everything is average, okay, to the n. Now, small n is going to 0, so I can develop this. So I get 1 over small n log of 1 plus small n log of z plus something which is of order n squared, average. Small n is small, so I develop the log. So I get 1 over n. If I develop the log, the first term will be n of log z average plus something which is of order n squared. And then I simplify the n. And here from this I get log of z average. And from the other one I get something which is of order small n, but n goes to 0, so I can forget it. Okay? Tell me if I did something wrong. It's possible. It's late for me. If I compare to Paris, it's okay? Okay, good. So now, for the moment, I didn't tell you why this is simple, okay? I just proved you that this is equal to this when n going to 0, but why this is useful. And the reason why it's useful is actually that this thing, it's easy to compute when n is an integer. So what I mean is that, it's easy to compute in general z squared, z3, and in general z to the n average. This is something that we are able to do. And so the replica method, what it does is that, what you do is that you compute z to the n average when n is an integer, and then you do the analytic continuation to real n, and you take n going to 0. And then while taking n going to 0, you just take this. You plug it inside this. You take 1 over n going to 0, and from this you get log of z average. Okay? So what the trick is really that computed this for any integer is easy. And then the difficult part actually is to do the analytic continuation, because this in general is not well defined. Okay? So this is why, well, at least at the beginning it was discussed a lot whether the result is correct or not. But now we know that the result, in many, many cases at least, is correct. We know it in the sense that it has been proved rigorously. But it's true that in many cases, if you face for the first time the replica method, you can wonder, okay, if I know, from the mathematical point of view is, if I know all the moments, all the integer moments of the random variable, do I know the law? Well, sometimes yes, sometimes no. It depends on how the moments behave. Okay? And in general, in the case which are interesting for physics, the answer is no. In general, if you know all the moments, you don't know the probability of z or log z. But still, well, what is behind the replica method is a way really to do the correct analytic continuation. Okay? Yeah?
Yeah, for replica method, in the context of Anderson normalization, it's very open. When constructing the field theory, you need to really work on like a large number of replica.
Yeah.
And then just treat as a trick and continue it to 0. I'm curious for glass, do we encounter similar issues?
So okay, for glasses, but I think I'm not sure it's clear if I say it now, but in principle, the replica method is defined in such a way, as I define it here, what you have to do, you do the small n limit. When I define it here, I do the small n limit before the thermodynamic limit. But actually, what we always do is the opposite. And actually, it's good that we do it in this way and not in the other, but okay, I think with this we will discuss later. Okay? So, this was just, a very an introduction of the idea. And now, I prepare an homework about the replica method, because I think that, for people that never did the replica method, the best thing is not that also because I don't have much time with 4 lectures, but in general, I think it's not good that maybe I present it to you already in the, let's say, in the best way possible, in such a way that you just avoid all the difficulties. So it's better that I give you exercise, and you try to do the exercise, and then in this way you will understand how it works, and also, what are the difficulties. So in the homework, there are 3 exercises. So the first 2, if you never used or almost never used the replica method, you're really encouraged to do it. So in this way, you will learn. So the first one is very easy. And the second one is nothing else that finding exactly the same result that we derived today for the random energy model, but with the replica method. And then instead, if you already have experience in the replica method, then do the third one, because this, it's instructive. Because, if you are, too much use and you think the replica method has no problem, works, and there is no, let's say, ambiguities, do the third one just to be a little bit uneasy. Okay? And so, as I told you, if you want to really learn the technique, you should do the exercise. That will be something useful. And I'm here, all the week, so we can discuss whenever you want about the exercise. So, thank you. Questions? Huh?